So good evening everyone. Day 2, session 2, Yan course. I request Dr. Ramesh to deliver his lecture.
Thank you, Professor Yadav. Okay, so continuing on to the climate change influences on hydrologic design, I also thought that dam safety is very important, and there's a lot of studies now which are focusing on the impact of climate change on dam safety. Anytime you look at the dams, we need to do two things. One is the operational changes because of climate change. The second one is the safety itself. If the hydrologic structure like a dam is facing any other issues because of climate change. So we're going to discuss that a little bit in this class. Okay, so recently we have seen the AR6 report, that is the 6th assessment report from IPCC, and of course they have synthesized all the main observations they have seen. The main idea is that human influence has warmed the atmosphere. There's unequivocal evidence about that, and the climate is already affecting many weather extremes in different parts of the world. We have seen that in the last 25 years, and so global surface temperature continues to increase, considering all emission scenarios, and heavy precipitation has become frequent, and it has direct relationship with global warming, because more hotter air can accommodate more water vapor or water, and that is causing heavy precipitation. And of course, many changes due to past and future gas emissions are irreversible for centuries to come, and we are seeing increases in sea level rise and other issues, and of course the intensification of severity of different events. So the natural drivers and internal variability will modulate. For example, climate variability always exists in the form of different types of natural patterns or oscillations. For example, you have ENSO or IOD, PDO, AMO, NAO, or AO, and so on. All this will have some effect on the oscillatory nature of the cycles. We call the dances of the climate. So that is always evident, but on top of the climate change signal. And then, of course, we have a number of concurrent multiple changes are happening, and that is going to affect our hydrologic infrastructure and so on. And extreme events are causing issues. Ice sheet collapse, and then of course glaciers are melting and so on. So all these things bring to a point where we need to consider climate change as an important factor, even for future design of dams, as well as rehabilitation of the dams, as well as also looking into mechanisms in which we can operate the dams, especially when climate change is affecting. So here are the most recent headlines from United States, and you can see that climate change raises risk of dam failures. Many reservoirs in United States, especially on the west, are facing low flows because of the droughts, and then that is posing a huge problem on the hydropower production. In some places, the hydropower production is very important for sustaining electricity in many cities. For example, Las Vegas, California. In many cities, you need hydropower generated, and that is threatened by the climate change, especially the reoccurrence of droughts with higher frequency. And sometimes the question is also being asked, is hydropower renewable or energy or not, because of the issues the dams are causing. And there are also challenges in terms of maintaining the water levels so that we can get the corresponding heads for our turbines or for our hydropower systems. So again, that is also causing some problems. Dams also contribute to global warming. This is a news to many people, but the sediments which come into the dams help microbes to survive, and these produce methane, and that methane is not really captured by instruments because we don't use instruments throughout the water inundation area of a upstream of a dam. We don't use that, so therefore many studies have neglected, or at least unfortunately could not monitor this. But the most recent studies have started to see that dams are also kind of increasing the methane production, which is also polluting the atmosphere and also leading to global warming. They actually contribute around 4% of the global greenhouse gases emissions, and which is equivalent to what our aviation industry commits. And then, of course, some other animals are also contributors of the pollution. Some advantages of the dams they have seen in the past. So, for example, previously, before dams were constructed, the sea level rise was increasing, but then the dams started construction in 1940s. That really helped to control the sea level rise because we are storing tremendous amount of water. But of course, this is one study which is indicating that dams might have positively contributed to reduction or limitation of our sea level rise. So why we need dams? Of course, there are different types of dams which I'm listing there. You need dams because you need for reliable sources of water, reduce the spatial temporal availability of the water. Large dams, of course, lead undesirable impacts, socially and politically controversial. We need water security. Of course, we need capital intensive investment because we need to invest in the whole materials and structure. Of course, that's a lot. But dams also are known to change the regional and continental scale hydrology depending upon the size of the dam. Okay. And of course, we know the operational uses of the dams, many for water supply, recreation, navigation, power generation, flood risk management, water quality management, irrigation, and of course, space for fish and wildlife. So all these are operational uses of the reservoirs. So some definitions, again, we know that probable maximum precipitation, which we use for design purposes, we get the probable maximum flood. And there's a difference between reservoir and a dam. So a reservoir is the water impounded by the dam in which water can be stored. A dam is the structure itself. It's the artificial barrier which we build using concrete or earthen materials. Typically, we have rule curves. You must be familiar if you're working in reservoir operations or management. These rule curves are defined by different guidelines. Even in the United States, we have rule curves. And these rule curves are religiously followed by reservoir operators unless there is an extreme emergency situation. That's when they try to change them a little bit. But these graphics are available, the rule curves for the operators. So these days, there is more assessment of the risk because the risk is something which every agency who's maintaining the reservoirs or dams, one and the same, trying to understand if there is higher risk dams or lower risk dams, and how do we estimate the risk, because there are both climatic factors and non-climatic factors, and the probability of occurrence of a specific catastrophic event, and then of course the amount of damage a particular event will cause. That's what we call it as consequence. So therefore, nowadays we are considering the triplet scenario, probability of occurrence and the consequence, and then of course the estimates of the damage. Okay. So if you see here, the construction of the dams, and we are going into 2010, these colors indicate how old some of the dams are, and you can see most of the dams are in either light green color and a blue color, indicating that we are still building dams, and there are so many dams that are being operational in the most recent years, and some of them are old constructions. So you can see how many dams each country has. China has the largest, 23,000 approximately, and then United States, and then India ranks third in the number of dams. This is from the ICID, And you can see the spillway capacities also. The largest spillway capacities are coming from India, and you can see that that is going to get affected by climate change in future. The multi and single purpose dams, of course, you can see that we are constructing lesser and less as we go, but we still have a lot of dams which are both multi and single. And mainly dams are built for irrigation. The second highest priority is hydropower, water supply, and then finally the flood control. So you can see here the single purpose is around 47, which is mainly for the green, that is irrigation. And for multi-purpose, again, it's irrigation, 24%. And then the other one is the earthen type dams are more prominent. So climate change is a bad news according to many environmental activists. They say that dams destroy habitats, they create earthquakes, they create consequences are too bad for dams due to climate change. And then dams also generate greenhouse gases. So it's a combination of effects of dam and a climate change that might result in bad news. So this was a recent study by a researcher talking about how much the people are willing to pay for new dams. So depending upon whether they live in a dry zone where they see benefits from the dams, there is a higher willingness to pay for the dams. Whereas the other cases where there are high wet zones, where there are dam impacts, then there is a paying money to demolish dams is happening. So this is their willingness to pay. Of course, it's based on survey, but again, you can see that how the attitudes towards dam building and dam demolition are changing. So here's an example how the droughts in United States are happening. This is a couple of dams in Colorado River, and you can see that it passes through different states and provides a lot of water for Utah, Nevada, California, and Mexico, and that really is a lifeline for many states, both for water supply as well as electricity. And you can see how much the Lake Mead, that is here, the Hoover Dam is one of the largest dams in the country, and it holds a tremendous amount of water, but then you can see how the Lake Mead, the water levels are receding year after year, and the droughts are forcing these water levels to recede. You can see the Lake Mead levels that is near the Hoover Dam, and used to be around 1,220 feet. Now it is around 1,054 feet. Approximately a good amount of 200 feet reduction in the levels of water can be seen. So that's definitely an impact for both hydropower production, recreation, and water supply. This again is another one, Lake Powell. You can see the reductions in the water areas over last 20 years. We also have a drought monitor where we monitor the drought on almost on a daily basis. We provide this information to the users, which can tell us in which parts of the country are in a drought mode. This was the most recent image, probably a month back, and you can see that a large portion of the West, California and other areas are under drought. So the questions we have to ask in case of climate change is that, will dams be effective in future as they have been in past in providing all kinds of services under evolving climate? The natural flow disturbance by dams, can we sustain that problem? Because when we build dams, we are altering the natural flow. So these days there are more push for restoration of the streams downstream of the dams. So they are trying to operate the dams in such a way that the water downstream is restored for aquatic habitat and other reasons. If you remove or build dams, what are the consequences? Do we need to change the design methodology considering the non-stationary climate? And how will the evolving climate will lead to cost sustainable options? These are several questions we have to ask. Of course, we know that so many things are happening because of climate change, frequency and intensity of droughts, changes in precipitation frequency and intensity, reduced snow cover, changes to soil moisture, and all these are contributing to floods. And there are modes of failure which are definitely, some of them are increased by changes in climate. Not all of them, of course, but you can see that some of the ways an earthen dam can fail based on piping or based on cracking or seepage and so on. And this is resulting of the humidity or kind of dry and wet cycles that cause the piping effect, or changes in the moisture content within the core as well as the soil matrix of the earthen dams. Similar evolution of different piping system, piping damage through the earthen dams. And of course, this is just earthen dam failure modes, but you can have failure modes for other ones also. You can see that currently around 90,000 structures are there, and many of them are privately owned, and the average age is around 61 years. And you can see that there are some state regulated, most of it is state regulated, and then of course only 6% are from the public. So here's an example of a recent failure of a dam because of extreme rainfall events. There was 5 inches of rainfall in 2 days, and this is the amount of flooding they have seen in May 2020, and requiring thousands of people to evacuate in Michigan. This is a very famous case of Oroville Dam in California. This basically the main principal spillway gave away because of extreme amount of water coming into the system, and the principal spillway could not handle the amount of discharge from the dam. The emergency spillway was also instituted, but still there were some problems, and then there's a significant portion of the spillway was damaged. And you can see the amount of rainfall in different parts of the California during that time, including the location of the dam. That contributed to the increase in the storage and amount of rain that happened, and how much the storage just went up because of the rainfall event. And these are the inflows, and you can see that there was tremendous amount of inflows coming in the last few days before that particular event. This is the emergency spillway, and the damage has happened in the main spillway, which you can see here. This is what has happened. So this is your dam, and then you have the principal spillway, and this is where the water started gushing out over the emergency spillway. They tried to repair it. There is a significant amount of erosion, and they tried to use some kind of immediate measures, but that was not helpful. So you can see here, this is the main spillway discharging the water, and then the emergency spillway is also discharging water during that heavy flooding event where the water reached to the brim of the now this was the damage that was done to the spillway. You can see how much amount of damage that caused because of the extreme release of water from the principal spillway. This is another dam which broke because of ice jam, where the ice blocks of ice started to move in because of a heavy rainfall event. And then there was a frozen river that was initially a frozen river, and then there was a cyclone also. We call it as bomb cyclone. Dropped tremendous amount of rain, and then finally this dam gave out, and then the whole thing broke, and then we lost several people as well as damage. So the risk factors: population increase, economic development, and of course, how do we adapt to water management? The main loads are discharge. So depending upon the return periods you calculate, you can see how much load comes onto the dam, and then we need to evaluate how much the dam is going to affect by that extreme event. So if you see the flood protection perspective, the operation, so what happens if you have extreme precipitation events because of climate change? Increase in flow, flood risk will increase, structural damages will happen to your structure, additional storage requirements are needed, increase in the sediment loads, and then you can also see reduction in the storage because of sediment loads and blockage of spillways. Of course, extreme temperature will also cause structural stability issues, and because the temperature is very good, then there will be increased vegetation that might block the spillways. Now, how is it going to affect the hydropower generation? Increase in inflows, of course, flood risk damaging the hydropower infrastructure also. Operation decisions will reduce the storage to accommodate flows. Hence, you can reduce the electricity production because you're trying to accommodate the new flows. You are reducing the storage, so the head is reduced, and then that will impact the hydropower. So power outages and then sediment loads can impact the infrastructure of turbines and penstocks. But if you see the lower end, if you have low flows, then again, hydropower production will decrease, and then water allocation for different uses will need to be reevaluated. And if there is extreme temperature, then we don't have problems at the reservoir end, but we have increases in demand for electricity, and that increases the pressure on how much electricity you can produce from hydropower systems. Water quality, extreme temperature, again, will change the water quality. It will introduce thermal pollution. Aquatic habitat may die because the receiving water temperatures are high. For water use, agriculture, drinking water, and water quality, extreme precipitation will increase the sediment load. So that means we are adding more treatment costs. And then, of course, risk of overtopping, pollution risk, suitability of water for use, because now it is more sediments because of the increased flows. If the reduction happens on the other side, you cannot sustain water for the agricultural use. Low flow augmentation, which is generally regarded as a measure for reducing pollution, that will not work. Recreation effects will be, uses will be affected because you don't have enough water. And then we have to use some kind of operational changes. So depending upon the type of construction of the dam, you will have different changes. You can have piping failure, overtopping, and so on. So these were now introduced into the risk assessment methodologies. Previously, these were not considered because the climate change effects were not considered, but more and more dams are failing. And you'll see in the end how many dams are failing because of the climate changes. The clay core construction will have similar problems depending upon the type of soils you are using for the clay core within the earthen dams. And then, of course, the dry and wet cycle periods will have effect. Increased cracking may happen, and loss of vegetation cover that will make erosion problems, and all kinds of things that will happen for different types of core or earthen dams. Now, in case of concrete dams, you have the similar problems because the wind and wave action can impact the structure, the concrete, expose the liner, block cracking when concrete cracks because of that, drying of the asphalt, and then instability, and also other issues because of the temperature variations. Masonry dams, the same problem. Exposure to sunlight may cause UV damage to the materials, and also the binding mixtures, thermal expansion, cracking and spalling. This has been noticed. And spillways, extreme events will cause spillway failures, increased transport of debris, and then damaging and blocking of spillway. We have seen that in the recent events. Also, the auxiliary structures which are attached to spillway or some other structures within the dam, they have increased transport of debris that will cause damaging components for the dams, and possible cracking of concrete channels and wave walls and metal elements, including the steel line. So design considerations, what has changed because of this extreme flooding? So there are a number of things which have changed in the United States. The revision of the PMP estimates is recommended by high hazard dams, okay, to withstand flooding, or use the best available science to update the PMP, maybe use a factor of safety on top of the PMP. The other one is more of a changes to operations. We call it as Forecast Informed Reservoir Operations, it's called FIRO. Now we have numerical weather prediction models which can tell us what will happen in the next 15 days. So that is what we are using now under a non-stationary climate, so that we can start planning for the operations of the reservoir. So here is a comment from the main operating advisor in United States Army Corps of Engineers, which maintains all the dams. So many reservoir operators and managers are instructed not to use weather forecasts as a part of their efforts to plan future management operations. Instead, water management were instructed to operate the principle of water on the ground. So it means that when you see rain, then only you start operating. There's no use of forecasting models into the future, maybe 10 days or 15 days into ahead, so that you can start planning for your flood which is coming into your reservoirs. That's why they started the concept of FIRO, a reservoir operation strategy that better informs decisions to retain or release water by integrating additional flexibility in operating policies and rules with enhanced monitoring and improved weather and hydrological forecasts. And you can see some papers already based on the FIRO concept, the Forecast Informed Reservoir Operation. So what they are doing is to look at the baseline conditions from the climate changes perspective, and then they incorporate the weather forecasts, and then they evaluate management alternatives, look for observations all the time, and then come up with what we call adaptive water control plan, and that's what it is. So here's an example of a rule curve. The rule curve is this one, the orange line, and then we can, instead of draining this water, depending upon the rainfall, we can save that water and try to see how we can accommodate that in our reservoir operations based on forecasted information. So this is FIRO. So you can see that these are the rule curves without and with FIRO. So with FIRO, the rule curve is much higher so that you can store more water, but without FIRO, it has gone down. So a 20% additional storage can be used, and that can benefit by the storage of water. The other problem we have is the atmospheric rivers. These are massive amounts of water vapor coming into this into the areas through orographic effect, where we have mountains which will drive the moisture up, and tremendous amount of rainfall happens. This we call the atmospheric rivers phenomena. It has been there for a long time, but recently it has gained attention because these atmospheric rivers every year are dumping tremendous amount of rainfall in one location, especially on the western side of the United States. And these are some kind of rivers. They look like rivers. They carry a tremendous amount of water vapor, and they come back onto the land, condensate, and provides huge amount of rainfall that causes mudslides and other issues, flash floods. So based on this, can we do something about the operational changes? Yes, we can do. We can do risk assessment. We can make changes to seasonal storage levels. We can also evaluate the ensemble-based inflow production models, which we can use it to improve our uncertainty assessment. And I'm going to discuss that in the last day about ensemble stream flow prediction. So what are we supposed to do? Long-term planning, reliable estimates into future based on climate projections. We have to use the right downscaling models so that we can project. Short-term planning based on forecast-informed operations. The forecasts of temporal lengths of oscillations are also important, because climate variability is also affecting your amount of rainfall and so on. So you might want to even predict what will happen in future about climate variability. Will I be in El Nino state or La Nina state? We can estimate that into future or project into future and do the planning based on that. And adaptive short-term operations, that will help. And of course, we need to reduce the uncertainties in future projections of the climate, and there should be some kind of trade-off. Compromise operating policies can be developed, and we have to develop more than one objective, because now the reservoirs are operating with multiple objectives, so we need to do that. And data collection efforts need to be improved, and the connections between different ecosystems, natural bodies, social, economic, urban systems, and health, water, everything is linked. So we have to do that, just water, but we have to also evaluate impacts on the other. And of course, the reliability, resiliency, and vulnerability of every system that is attached to the reservoir system should be evaluated. And we also talked about the level of service, how much service the reservoirs are giving, the level at which they are giving. That also need to be important. And then finally, when we are talking about reservoirs, we need to make sure that we attach the what you call management of the water in such a way that we are mimicking the natural flows as much as possible. We need to work on sediment management and low flow management. FIRO is one of the approaches that has been used so that we can use the quantitative precipitation forecast. Remember, we talked about quantitative precipitation estimates yesterday. Now this is quantitative precipitation forecast. Standing now, you can forecast for next couple of days, and you can start thinking about adaptive operation. And then, of course, the ensemble stream flow forecasting approaches. So, of course, based on the projections, we have to think about how to protect the infrastructure, reevaluation of the design standards, changing of your intensity, duration, frequency relationships, changing of PMPs, changes to your operations, and so on. So in the end, of course, the risk assessment is also important. We need to go ahead and look at the risk assessment and upgrade the existing power plants. And of course, we are going into what we call pump storage plants. So what we are doing is we are generating electricity based on this upstream upper reservoir at a different height. We generate electricity during the time when there is more demand. When there's less demand, when the energy price is lower, we push the water back again into the pool so that we still retain the head. So this is the big thing now, and most of the pump storage hydropower systems are coming in place in the United States. You have the same pipe working as a pump as well as turbine. So whenever it needs to generate electricity, it will use a turbine. Whenever it wants to use to pump water into the upper reservoir, it will use it as a pump. And this is again the same configuration. We have around 50 pump storage plants. We are adding more. And if you don't want to use the same some electricity for your pumping of water into the upstream reservoir, you might want to use solar energy to use that power to make it to pump the water onto the top. And then, of course, the adaptive operations. So basically, based on the system configuration, we will know exactly what we are trying to achieve as the time progresses. So we are improving the forecasting systems by knowing the state of the system as we progress into the time. We call it as adaptive forecasting. So 3 things they are doing: rehabilitate, retrofit, and remove old dams. And then there have been agreement because there's more emphasis on the environmentalists as well as the reservoir management agencies, trying to see that what amount of data is available, how much we can use alternative technologies. And of course, relicensing, licensing, and so on. These are very important because many of the dams in the United States are operated by private entities. And classification of the dams, depending upon high potential hazard, low hazard, and significant hazard.
Sir.
And of course, yes.
There are 2-3 questions. Shall we take it first?
Yeah, I'm almost done with this part.
Okay.
Then,
okay. So first you finish, then afterwards we'll take the question.
Yeah. So again, the PMP definition and PMF definition is changing. They would like to incorporate that into this into the new hazard classification. And extreme rainfalls are also a huge problem. They introduce hydraulic stresses, including the spillways, overtopping, and so on. And you can see that the number of failures from 2010 to 2019 are the overtopping is the main one, piping, spillway failures, spillway erosion, and some of them are gate valve failures and so on. So you can see that the maximum is because of the extreme flows which are coming and overtopping of the and dam failure incident driver. So once the dam fails, of course, the main driver is the hydrologic system conditions, as well as it is causing the flooding, which is main drivers for dam failure. So there are risk components for different different climate change impacts, which will need some assessment methods. So we need to do all these assessments for considering flood, reservoir levels, gate performance, failure modes, flood routing strategies. Those also need to be developed because if you want to move the water around, and outflow hydrographs and socio-economic consequences. So these are taken from the United Kingdom flood assessment report. These are available, and also they are one and the same what I have discussed, but they are providing in the form of a table, so I thought they'll be useful. So please go ahead and ask questions. Maybe I have a few more things to discuss as we go into the next section. I will talk about them. Please go ahead and ask questions.
The first question is asked by Deepak. Sir, you mentioned storage increase in the dam. How is that possible, as the storage may decrease due to sedimentation?
Storage increase in the dam in the sense that whenever there are extreme events, some dams may have sediment as a part of their flow, but some dams may not get so much sedimentation load. So increased rainfall will increase the increase the storage beyond a threshold limit what each dam would have fixed. For example, the Oroville Dam, sudden increase in the flows has reached the water to the brim level when the principal spillway started operating, and the water is too much even to be released from principal spillways. They have to use the emergency spillway. So even emergency spillway was kind of automatic. It was not constructed properly, but they thought principal spillway can handle it. So in some situations, if the flow is so fast, the sediment load is there, but not necessarily so much as opposed to water which is filling the storage. I hope that I answered the question reasonably okay.
Deepak, is it okay? You can unmute yourself, Deepak. Sir,
Yeah,
the second question is from Rashmi. She is asking, how difficult is the operation of dams due to extreme precipitation events?
The main issue is that what we have seen in many failures within the United States or problematic flooding issues is that the lack of forecast of two things. One is the watershed conditions before 10 days or 15 days before the actual failure of the event, and the precipitation forecast. So if the precipitation forecast is available, for example, if atmospheric rivers are coming in your way, which are going to dump a tremendous amount of rainfall, then you have a reason to believe that you have to operate your dam in such a way that you provide extra enough storage. So the reliability of the forecast and the reliability of the soil moisture conditions will really help how much amount of water that will come into your dam. If we can forecast that with some level of uncertainty, it doesn't have to be exactly accurate, it cannot be a deterministic forecast, it can be a stochastic one, but at the same time, if the operator knows that the probability of this much water coming into the reservoir 3-4 days in advance or 10 days in advance, that would be good, because that's when they can start operating the reservoir in such a way that they can provide storage for the incoming water. So now the accuracy of the forecasts have become much better, because now we are using numerical weather prediction models, NWP, we are using radar data, we are using all other data available to make a very good quantitative precipitation forecast. So if we can make 10 days in advance what might be expected precipitation in that region, combined with the soil moisture conditions at that time, then we can simulate different scenarios and go for the scenario which can be highly probable, and then try to operate your reservoirs in such a way that you can accommodate the incoming flood. So that is what the forecast informed reservoir operation strategy was doing. It is built to do that job for most of the reservoirs, and they have done pilot studies. They saw that improvement, and now they are going to replicate to all other reservoirs to improve their operations. Now, the crux of the whole technology is to have accurate forecast. If your forecast is wrong, then the possibility of you releasing extra water just to create storage for incoming water may be catastrophic, because in some cases the reservoir operators thought we might get a flood and then we have to release the water. When they release the water, the flood didn't come, the anticipated flood didn't come, so then they have problems with water supply and irrigation. So the accuracy of operations, the viability of operations depends on the accuracy of the forecasting tools you are using. I hope I answered the question.
Sir, how many days ahead the forecast is done in US?
We do 3 types of forecasts. We do 1 day, 3 day, 5 day, 7 day, 15 day actually. So not 3 more, but of course 15 days are very long term. But short duration can be 1, 3, and 5 days. So sometimes that enough information, enough lead time is also not enough. But then in some cases, the operators have a lot of control on releasing the water to create more storage. Or if the reservoirs are in series, then they can come up with a plan to see how incremental storage options can be done. For example, one reservoir stores more water than the other one, so that they can combinedly handle the flood which is coming. But the most accurate or more relevant are 5 day or 3 day. At the closer, the smaller the lead time, the more accurate the precipitation forecast will be. But there are long-term long-term precipitation patterns. For example, if you see a hurricane coming in, then you have a lead time of 15 days or 20 days. You know the strength of the hurricane, you know how much water it's going to dump, and you know how to manage that water and then operate the reservoir. The other important forecast, which is very critical, is the soil moisture levels in the upstream stretches of the reservoir. If your soil moisture is accurate, then you have a better understanding about the flood. Okay.
But sir, in case of extreme precipitation, like it happened in case of 2006 for Tapi basin, that
okay.
the inflow was much higher than that of the storage capacity of the dam, total capacity of the dam.
This is what happened in Oroville Dam also.
Oroville Dam also this happened. Okay.
Yeah, because that is possible, because sometimes if you don't have the lead time to reduce the storage to accommodate the incoming storage, then we have a problem. So for example, this is your Oroville Dam. You can see the water is at the brim of the topmost height of your dam. So the water starts spilling from your emergency spillway as well as the principal spillway. So you cannot do anything unless you have a good tools to have a reasonable forecast in the next 5 days at least, or 10 days. So that can help us in creating additional storage. And that's only possible by improving the accuracy of your forecasting tools. Forecast is never perfect, but at least you can improve. But The other factors which were never considered based on the report which came out, you can search for Oroville Dam failure and other dam failures. There are reports available publicly. The other factor which came out, very important factor came out, is the ground conditions, the soil conditions in the upstream. So if there was some rain before this big rainfall event, the soil would have been already completely saturated, and that would have caused additional flooding. So some events are inevitable, but if you have forecast with a good lead time, for example, in Japan, they use numerical weather prediction models almost on a daily basis. They use, because they have typhoons like small hurricanes and extratropical storms coming into their area. And the Japan area is very small compared to United States, the very thin stretch of land. So they have huge impact, but they are able to operate their dams to reduce flooding by effectively implementing the storage patterns based on the numerical weather prediction models, combined with any other type of information, so that you can improve the forecast. The second thing is, as the forecast happens, as the time progresses, you adaptively improve the forecast by using the new set of conditions, so that you are providing more information to the operators so that they can release the water in advance and try to protect the structure, as well as create enough storage so that the dam will not fail by overtopping or any other failure mode.
Sir,
yeah, any other questions?
Other issue is that when we release a huge amount of water through spillway or emergency spillway, the downstream side river may not have the carrying capacity equivalent to releases from the dam. And almost all the cities in India which are on the downstream side of the dam get flooded in such cases when there are heavy releases from the dam.
Yeah, so this heavy release, what you are talking about, is done when your reservoir is almost flooded with heavy amount of water.
Yes, sir.
But what I'm talking is that preemptive action. So if you have confidence in the forecast given by the numerical prediction modelers as well as meteorologists, then one more thing is, you need to have ground level sensors to see the land conditions. So if you have enough confidence, then you can do a controlled release of water, and that's what many countries do, including Japan and even United States now is doing what we call a controlled release. A controlled release so that the downstream channel capacities are never exceeded. So you release the water slowly over a 10-day period and create that extra storage that might be needed for the extreme rainfall event. So it's more of a preemptive action. Once the water comes to your reservoir, fills up the reservoir, we can't do anything. And that's what happened with Oroville. See, the people were waiting for, they were thinking that maybe they will not have a lot of rain because we are not seeing rain in the last days. They have not monitored the soil moisture conditions in the upstream of that particular reservoir. So they were not anticipating certain amount of rainfall which this event has caused. So, and they were confident that the spillway can be used to transfer the water from upstream to downstream, but unfortunately the spillway also failed. So in a climate change situation, what we are encountering, we will be encountering more frequent heavy rainfall events. So that means we need to have in place a planning for not only for forecast, but also planning for what might happen, like a seasonal forecast, depending upon ENSO, or for example, in US, we have a forecast for hurricanes, the number of hurricanes we might get, or number of cyclones we might get this year. So we have that forecast. We also have the extent of the rainfall that might happen in that season. So all these indicators should help the reservoir operators to see that how they can effectively reduce the storage to accommodate the incoming flows. So that is, I think, the whole idea is in that forecast informed reservoir operations. That's where we have to build it.
Sir, the next question is by Ayushi Panchal.
Yeah.
She is asking, dams are backbone of developing countries as far as
Yeah.
food grain production. How
Yeah.
does the climate change impact it?
Oh, yes. I mean, the climate change main problem with the we need a lot of dams in developing countries because of the either controlling the spatial and temporal variability of the water, irrigation, water use, water supply, and everything. But the problem with that is that we cannot build large dams these days because of the issues related to environmental concerns, inundation in the upstream. So large dams cannot be constructed. But when you construct small dams, which are okay from environmentalists, but the problem is small dams cannot have enough storage. So there are mechanisms by which you can try to improve the operations so that you can sustain the water. But every part of the operation, structural stability, has to be considered based on the climate change or even climate variability. For example, right now we are in a kind of mild El Nino, or so now seasonal forecast for the next 3 months has to be done to see how much water we are expecting, and are we expecting too much or too less. Depending upon that, you need to modify your operations. So one is construction of the dams, which are environmentally sustainable. The second one is after the dams are constructed, how do you manage them under climate variability and climate change? So these are definitely a challenging problems, but structurally we cannot do much, but operationally, yes, we can do by looking at the forecast, by doing some kind of stochastic modeling, or by doing probabilistic modeling of the flows that might come in. What are the scenarios, scenario-based analysis, and then see that how much water can be released without affecting the future storage of the users. So for example, if you are one time it happened in Florida where we released more water than that can be released because we were worried that hurricanes will bring more amount of water. So more amount of water was initially released. Now the hurricane came but did not create so much amount of rainfall. In the end, we ended up having less amount of water in the reservoir, where we had to go through some kind of rationing or some kind of control where we cannot use water for our lawns and other purposes. So it is a double-edged sword. We have to be very careful in how we address the operational issue. New construction of the dams, that's a completely different story. But right now, we need to see how we can benefit from climate change information, climate variability information, improvement in weather forecasting models, improvement in precipitation forecasting models, improvement in ground sensors, improvement in soil moisture sensors, and the conditions of the landscape. If we can do all those things, then we can effectively reduce the water stress and also stress on the reservoir operators as well as the people who are relying on water supply.
Sir, the next question is from Abdullah Salim.
Okay.
He asks, can we apply modest cloud level 2 data and downscale the rainfall estimate to 2 or 3 kilometer resolution?
Yes, you can do, as long as you can make sure that the downscaled data sets are reasonably representing the spatial variability you are looking for. So you should have enough ground truth to double check, and if you can downscale it, double check with the ground truth and probably apply some bias corrections, that product can be used. Any product which is evaluated against a ground truth can be used. provided we do some bias corrections. Any other questions?
Sir, that is the end of the questions.
Okay. So we meet in 15 minutes or how?
Yeah, sir. We'll have a break of 15 minutes, and then afterwards we'll start our last session.
Okay.
Is that okay, sir?
So yeah, that's fine. 15 minutes is fine. We can start. So right now, what is the time now?
6:05.
6:05. So yeah, we can start 6. We can start in 10 minutes if it is okay.
10 minutes. Participants,
Or if you want.
Participants, you want to have more time, or will it be good that we start in 10 minutes?
So that we can leave early.
Yeah.
Sir, I have one question.
Yeah, please.
Okay, go ahead.
Yes, sir. Sir, what is the significance of sediment forecasting as compared to stream flow forecast?
Yes. So as I said, you need to monitor the watershed conditions. There are two well-known approaches. One is the Russell, revised universal soil loss equation, right? Or USL, that is universal soil loss equation. So these are the two methodologies which will use precipitation as a input to find out how much sediment load we can expect from a given watershed of a given land use. So based on the precipitation forecast, you can input these precipitation values into these simple models and try to estimate the sediment loads which might be coming to your area, in the sense to your watershed, in terms of the flow which is coming. And that can help you to understand the sediment loads that might be coming from your watershed into your reservoir. And that really helps you to maintain and operate, and then probably look into the consequences of the loads which are coming in. There might be more advanced approaches. I'm not an expert in sediment hydrology, but these are some of the simple conceptual approaches based on land use, as long as you have a nice spatial analysis based models which can do all the calculations for you. You can actually estimate the sediment load. Did I answer your question?
Okay, sir. Thank you. Yes, sir.
Yeah. So sediment load is very important factor that needs to be forecasted, because not only just the water, the sediment load also has forces which are implicated on top of the reservoirs. So sediment load also becomes very important. Sediment load has a lot of damaging issues, so that needs to be also considered, especially in the heavy rainfall event scenario in case of climate change or climate variability. So that's a very important question you have asked. There is a significant impact on sediment load. So if you see the slides, what I have presented, sediment load comes up almost in every slide, indicating that it has a tremendous impact on your operations. Okay, good.
Okay, sir. Thank you.
Okay, so we'll meet in 10 minutes. Is that okay?
Yes, sir.
10, 15, yes, 10. We'll meet in 10 minutes. Yeah.
Yeah, sir. 6:20 will meet.
6:20 we'll meet. Okay, bye.